Hello, my name is Jacob Herrington. I'm the Automation Product Manager from Teledyne CTech Technologies. I want to thank you for attending today, and hopefully some of the information I provide will be useful to your lab in the future to simplify your sample preparation. So, what's so bad about sample preparation? Why is it such a burden on our laboratories? It's in many ways the bread and butter of our daily work, and it's something that's so commonplace you'd expect everyone to be able to do it successfully, or at least that's the hope. So what's the problem with it? Well, for the analyst who's actually doing all the pipetting, decapping, transferring, and so forth, they can spend a large portion of their day doing repetitive motion. And sometimes it feels like that maybe all they do in a given shift is move one rack of tubes from one place to another place, maybe type a little bit on the computer, and then go back to pipetting. This type of work can lead to low job satisfaction because it's at its core kind of boring. I mean, you're doing the same thing. That nature of the work leads to high turnover because it begs the question of, is this why I became a chemist? Is this why I spent all the time studying and going through school so that I could stand here and pipette all day? For the manager, it becomes an even bigger problem because the nature of this type of repetitive work leads to mistakes. Those mistakes can go kind of one of two directions. Either it becomes something like you've messed up a calibration curve or a QC sample, and thus is something that your lab recognizes as an error, in which case you have to go back and do more sample preparation and spend more time analyzing. Or, potentially worse, is you mix up sample preparation, and so when the data comes in, you don't recognize anything is wrong with it, and you send erroneous data to your customers. These types of errors lead to what is really a fairly common question in laboratories, which is who made the standards? Because when our calibration curves fail, and it happens in almost every lab from time to time, the question typically comes back not what's wrong with the analyzer, but who made our standards? And was it Billy? You know, we have two examples, and admittedly these are kind of far afield examples of analysts that you might see in a laboratory. And which one of those would you trust to make your standards? And the fact of the matter is, looking at them, you can't tell. A manager knows who their quality employees are. They know who the hard workers are, they know who's good at making dilutions, and they know it has absolutely nothing to do with physical appearance when it comes right down to it. But even the best analysts, they get sick, they take leave, they want to have their holidays, they have birthdays, they have off days, you know, they have their Mondays and their Fridays. And in the end, as a manager, what you look at is you're paying someone, whether it's your best chemist or your worst, you're paying them to stand essentially in one place for most of their day, kind of waving their arm back and forth, doing the sample preparation. It's tedious, it's time consuming, and when you get right down to it, it leads to high staff turnover, which becomes a major problem both in sourcing your staff and in training your staff, because you have to train them on your sample preparation, on your LIMS system, on any analyzers they work with, and that can become a very major problem for finding success in a laboratory. So this is an idea that I actually gleaned from one of my lab visits, which is every manual step is an opportunity for error. And whether that's you manually pipetting, you're manually typing something into the computer, you're transferring a tube from one location to another, every manual step along the way is a chance for something to be done incorrectly. And so what I would like to propose a solution to help minimize the number of manual tasks that need to be done in a laboratory on a daily basis. That's why we made the SimPrep. So what this is, it's a simple preparation station. That's given the name. It's based on CTech automation. Teledyne CTech has been making autosamplers for sample introduction for ICP for about 30 years, and we're recognized as experts in the field. We've combined our autosampler with a Hamilton microstation. Hamilton offers these little microstations as standalone, semi-automated dilution systems. And by combining that with our autosampler and a simple software package, we've created a fully automated solution for sample preparation. You use the same type of racks that you use on your ICP, which allows for quick and easy sample transfer after dilution to your analyzer for sample introduction. It has very simple, user-friendly software. A small mobile footprint allows for many different functions for your sample preparation, and is available for a wide variety of different liquid applications, including things like soils, mining, drinking wastewaters, coolants, even some USP applications. I want to show you a little bit about the software because I know we get a lot of questions about that. Really, the software is very straightforward. Most of what you work with the software is essentially an Excel spreadsheet. So what you see down here, this is a screenshot of your main interface page, and really this is a fairly complicated sample preparation. This would be for preparing a sample 3 different ways with 3 different final concentrations, and one of them having a standard spike, which is a lot more complicated than what most people would do. But essentially, what you can see here is you have, your positions, you have your original sample positions, your final positions, and then what volumes you want to put in. Everything's done in microliters by default. You can also put in your dilution information in like a 1 to 10 format or as 10%, and the software will automatically do the math to make sure that you get the right amount of sample based on your final volume. The software also allows you to optimize the performance of the system for your specific application. So that includes features like being able to put an air gap between your sample and your diluent to improve washout. It includes full customization of your sample wash, whether that happens at all or you can completely skip the wash step between samples, or you can have it use quite a large volume depending on what your goals are for your sample preparation. It also allows for customized probe depths and customized aspiration and dispense speeds to reach the specific goals for your samples. And there is sample homogenization options available as well. In addition to those, the software is generally flexible in terms of how it runs on a day-to-day basis. What you see on the left are essentially the icons that you can select for any given sample, and that allows the sample list to be easily adapted. So what I mean is that normally for a type of preparation, you would make a file that can prepare 60 or 120 samples, depending on your particular configuration. But you can use that same file even if on a given day you only have like 23 more samples, or at the end of your day you have an odd batch that doesn't fit nicely into 60, you can very easily adjust the existing file to go from doing 60 samples down to the desired 23. And then, while it's running, say you're on sample 12 out of the 23, if you have a couple more samples come in and you need to add those to the end, you can do that while it's running. And if you have a sample that comes in that's a rush that you need to get on the ICP because you need that data today, what you can do is pop it on there, hit Express, and the SimPrep will actually jump ahead, run that sample next, and then go back to where it was in the sequence, pick up, and continue going forward without missing a beat, allowing you to very quickly take that rush sample, put it on your ICP, and analyze it. This can be critical for rush samples or for samples that you realize need to be rerun later on. And the sequences are designed to be method specific, which means that you can very easily switch from one type to another simply by basically loading a different Excel file and open the this sequence that's going to be my ultra clean as compared to this other type of sample preparation that I'm doing. This is a brief video that shows kind of the components of it here and shows the system in action. So what you can see is we begin with a simple probe rinse. Now that it actually primes the lines. This makes sure that everything, all the diluent is fresh before you begin your analysis. If anything was left over from the last time the system was used, we get that washed out before we begin. Here the sample aliquot's pulled up and then the diluent's drawn. You can see the advantage of having 2 syringes. The smaller syringe handles all of the raw sample movements. That allows for you to get better accuracy and precision on your sample aliquot, while the large syringe handles the diluent, allowing for larger volume final samples. So you can prepare a 10 ml sample, but still have the accuracy of a 1 ml syringe when it comes to handling your sample itself. There's a variety of syringes available for this as well, so if a 1 ml and a 10 ml don't quite fit your application, there are other options available. And here you can see the system. We sped it up ×5, so you can kind of see the flow as it continues to go out, pull up an aliquot, and then rinse between each. Now the samples here are actually coolant samples. We specifically chose those because we knew that they would be visible for a video like this as compared to something like a water sample, which might be harder to see. And one thing I hope you notice is that the final dilution volumes as you go across the line are pretty much identical. I mean, they essentially form another line, and they should all be the same volume by the end. This type of system really helps to prevent errors that can happen through manual dilutions, such as pulling up from the same 50 ml vial twice. When you're dealing with volumes of that size, it would be really easy to take 2 aliquots from one tube and skip the next tube altogether and never realize what you've done. With the SimPrep, you have traceability to make sure that sort of thing doesn't happen. We often talk about dilution with the SimPrep because that is the most common application for it, but it can do more than just dilution. The system's also designed to do things like dispensing, in which case you can completely remove the rinse step entirely and simply go from one tube to the next, dispensing a predetermined amount of volume. It can be used for dosing. It can do serial dilutions. You can split samples, and what I mean by that is, seen here on the right, you can take one raw sample and prepare it multiple different ways for different analyzers or different needs or different parts of your application. This can be used, as you'll see later, for preparing the same sample and then preparing it again with a matrix spike and a spike duplicate to do that additional testing. It can also be used to make your calibration curve, even to 6 or 7 standards, fairly complicated calibration curves that would frequently require a second intermediary. The system can do that in an automated fashion. All right, now that we've talked about what the system can do, let's talk a little bit about how that applies to the EPA 200.8 methodology. Samples are generally diluted at about a 10x ratio. This reduces salt load, which can cause damage to your sample cones. It also minimizes interferences such as argon chloride, which is known to interfere with arsenic numbers, and a number of other matrix effects. This type of dilution is critical for getting the best performance out of your ICP-MS. However, it can also lead to laboratory contamination being introduced during the dilution step. And because of the low detection limits with ICP-MS, any contamination that comes from the process becomes even more problematic. Dilutions are prone to error simply because we're all human, and at the end of a long day, when you're going to make a 50x dilution, it can be pretty easy to accidentally make a mistake in your head, do the math wrong, and instead do a 20x dilution. Now, that kind of mistake can be very difficult to trace later on, because, of course, if you think about it later or realize maybe you did something incorrectly, by the time you get back to check your pipetter, odds are good that someone else has already used it, and there's no way for you to know for certain what you did. However, with something like the SimPrep, you have a record of everything that you do. So even if you did happen to make a mistake and type the wrong number into the software, you can go back later and see exactly what you told the hardware to do by reviewing your sample list in the software. That sort of traceability can be critical for laboratories, especially in a high throughput situation. One of our local nature reserves was recently found to have high levels of manganese in their drinking water. We know this because when my family went there to go on a hike, they saw these signs up in the main building as a notice to anyone there that they shouldn't give the drinking water to any infants under 6 months of age or use it to make infant formula. Now, my family was slightly concerned about that because it is a beautiful nature reserve and we want to take care of our local resources. But when I was told about it, I frankly, and slightly embarrassed to admit that I got excited because it was a great opportunity for our lab and my application group to get a water sample from a local source that we knew had high levels of manganese in it, high levels of a metal for us to test and use in application work. It's really nice when you're doing this type of applications to know that you're going to have something other than water in your water samples. So when my wife told me, I said, well, that's great. We're going to have to go back and collect a sample so that we have plenty to work with going forward. This has proved to be very useful for application development, but also it allows us to see what the EPA testing showed with regards to the samples from this site. Once we had that sample, what we did a number of different tests on it, but specifically we used it with the SimPrep to show reproducibility of sample preparation. So in this case, we took the sample, we prepared it in a 10x dilution, and we did that 10 times by hand and 10 times on the SimPrep. We then ran those on our ICP-MS and compared the results across the 10 samples to produce an RSD value for the batch. What you can see here, the farthest on the left, that's our hand prep and SimPrep for those 10x dilutions. And the RSDs are nearly indistinguishable across the 10. Next to those, kind of right in the center, is actually our control. And what our control was, it was a 10x dilution made up in a larger 50 ml vial. That vial was then tested 10 different times to try and allow us to remove any variability that came from the sample preparation process itself and focus on what a baseline would be just for the ICP analysis. And as you can see, that came out very similar to what the SimPrep and hand prep results are, showing that our hand prep is good too, and the SimPrep and the hand prep both came out very nearly indistinguishable from the control. On the right was a slightly different test where we actually wanted to verify our RSD performance not only with a 10x dilution, which is a fairly simple dilution really, but also a 20x, a 50x, and a 100x. So we prepared those dilutions several times each and did the same thing. We ran them on the ICP-MS and gathered the RSD data for each set. And those, you can see the hand prep looks to be a tiny bit better, but really they're more or less within the error bars, as we can see on our control with the other group. The next thing that we wanted to do with this is we actually used it to do some spike testing. So here's a little screenshot from the software. You can see the LCS, that's our laboratory control sample. That was essentially just our standard diluted with a 2 ml up to 10x dilution. Then we have a raw sample, and then we did a matrix spike and a spike duplicate based on that initial sample A there with the same 0.2 ml spike for both the MS and the SD. The data from that preparation is shown here, or at least the readback is. And what we found was that we were able to get very, very good matrix recoveries with the spike and the spike duplicate. As compared here, they are to the LCS. Everything came within 90 to 105%, which easily meets the 200.8 criteria, and almost all of it's within 95 and 105%. We just had a couple that fell slightly below the 95%. So the data came back very, very good on those sample spikes. We also wanted to show the calibration curve. So we prepared, again, a calibration curve. This is a 6-point calibration curve made from a 100 ppb stock solution that we prepared both by hand and on the SimPrep via serial dilution. Both the hand prep and the SimPrep produced good calibration data, but the SimPrep had 0.9995 or better across all of the elements tested, whereas on the hand prep you can see a slight dip in the zinc and the arsenic numbers. We did have some contamination in our zinc sample, causing that to drop below 3 nines. Following the calibration curve, we ran an ICV, and then every 10 samples we ran an additional CCV to show the recoveries on those. The ICV is a second source standard, and it still came within 5%. All elements were passing, and that's across the entire duration of our run. And you can see that everything, the whole way across, easily comes within the 10% required acceptance criteria for EPA 200.8. And generally speaking, it was all within 5% recoveries. We also did some standard preparation with NIST standards because we wanted to show something that we knew had quite a few known values. If having high manganese is nice, being able to use a NIST standard is better. And so we have the NIST standards listed there. The really important thing here is the recoveries, is we're able to prepare these with the SimPrep and analyze them, and all of our recoveries came back between 92 and 103%. The two that are highlighted actually are highlighted because they came in, they had a measured and certified value lower than the lowest standard on our calibration curve for those elements. And even with that, they measured pretty much right on and have recoveries of slightly over 100%. So we're able to get some very good recoveries on the standards. This is actually from another study that we did where we were testing for the system for carryover data, or for carryover limits. What we did is we prepared a calibration curve from a stock standard of 100 ppm. We ran blanks at the beginning and at the end of the run to establish a baseline. We ran a blank, or prepared a blank directly after the 100 ppm standard, and then prepared a couple more blanks. But when we analyzed them on the ICP, we made sure to separate the preparation blank from after the high standard from when the high standard was analyzed itself. So the preparation blank was actually run after another blank to ensure that any carryover we did see would be isolated to the sample preparation and not the sample introduction. And what you see here is we're able to get very excellent carryover with none of these elements reporting over 0.00%. These are all percents. But the highest that we received was on calcium, where we did get a 0.02% carryover. But generally, the carryover was very, very negligible. In summary, the SimPrep is a fully automated sample and standard preparation system. With plug-and-play installation and easy-to-use software, it's very customer-friendly. And there's the option to use the same autosampler for both your sample preparation and your sample introduction where applicable. You can move sample racks directly from this autosampler to your sample introduction autosampler for analysis, and it's available for all aqueous sample types. Thank you.